Okay, we have this thing called the factorial, and it is simply a mathematical device for counting things, and it's defined as the product of basically a decreasing series, and then you always terminate it with 1. So, for example, if we had 3 factorial, that would just be 3 times 3 minus 1, which is 2, times 3 minus 2, which is 1, and we'd be done. And so if I have 3 things, say A, B, and C, then there's 6 ways that I could arrange that. I could have ABC, that would be way number 1. I could have ACB. I could have BAC and BCA. And we could have CAB and CBA. And that would be a total of 6 ways to arrange those 3 things. So that's just the fundamental counting principle. You can read about that in your book and everything, but let's look at a little bit more advanced formulas and hopefully help you understand how they work a little bit better. So let's take a look at this permutation formula, which is NPR, not to have anything to do with the boring radio station. Just kidding. And it's defined this way, where N is the number of things and R number of things selected. That's what that's about. And so N factorial would be the number of ways to arrange those things, and N minus R factorial would be the number of ways to arrange what's left over. All right? And so let's consider something like 3 things taken 2 at a time. In the formula, it would just work out this way, which is just 3 factorial over 1 factorial. Well, 3 factorial is simply 3 times 2 times 1, and 1 factorial is just 1. So you just get 6 out of this. So there's 6 unique ways to arrange that. And so we already have shown how 3 things can be arranged 6 ways. But if I take them 2 at a time, what would that look like? So let us recreate our set of things here. So if I take 2 at a time, so there's an AB, there is an AC, and there is a BC. But you also have BA, CA, and CB. So you still have 6 ways to take 2 things at a time and use them up. That's the permutation formula. So we can give that a name. Permutation formula. And so that's what you use when you want to count the number of ways to arrange some set of things when you take so many of them at a time. Now let's talk about combinations. So there's this combination formula, and unfortunately the way most textbooks give it, they don't clue you into the fact that it's really the permutation formula divided by the number of ways to do your selections. And so let me show that math a little bit. And so what this means is that the combination formula just boils down to basically the permutation formula with 1 extra factor. Now the trouble is by failing to show you that the combination formula is simply take the number of permutations and divide it by the number of ways to arrange your selection, you sort of lose track of the fact of why combinations eliminate order. And so what I want to try and show you is how that works out. So let's take our set of things A, B, C. And remember, if I take two of them, I have AB, BC, and AC, which is the same as BA, CB, and CA. You still have those 6 things. That's the number of permutations. So this would be um, our NPR set, if you will. Now, if I take, since I'm taking 2 things at a time, so um, let's do 3, choose 2, count the number of combinations. So that's going to be 3 permutation 2 over 2 factorial. Well, we know that that's 6, and we know that that's 2. And so you'll have 3. So what you did in this case here is you divided out the order. And that's why questions that don't concern themselves with order, but they're still selections, how many committees can you make from these 7 people or something, that's why you use a combination, because basically you're saying A, B, and B are the same, B, C, and CB are the same, and so are those. And so you really just have 3 things, 3 combinations when you don't care about the order. But if you do care about the order, then you have 6 permutations. So I hope that little tutorial helps you separate the two. Key idea is that combinations are dividing out the order of the selection in a permutation. If only the books would just say it that way. Cheers.